have done at the end of Calculus 1, starting in sections 4.9 through the end of chapter 5, you did integration. And so a lot of what we do in Calculus 2 is based on integration. We do a whole lot of integration. And so what we're going to start with today is just a review of some basic integration techniques. And then we'll move on, we will move on to additional integration techniques as we go. Now, we do several different things in Calculus 2. We do integration techniques, we do applications of integration, we do sequences and series, power series, and then we do chapter 12, which is kind of a variety of things that you'll need for Calculus 3, but not necessarily dependent on things that you did before. And so unlike Calculus 1, Calculus 2 is a bit more independent, if you will. You know, in Calculus 1, everything builds on itself. And Calculus 2, there are 2 or 3 different sets of topics that, while being related, they're quite different from each other. So the first several weeks, we're going to talk about integration. And so first things first, what are we doing when we're integrating? We're reversing the differentiation process, right? And so these first 17, and there are actually 3 more a little bit later, are integrals that you should know already, except for this one and this one. We'll get these 2, let's see, in about a week or 2. Okay, so 15 and 16 are not integral forms that you've probably seen in Calculus 1, but the others are integral forms that you should have seen. And so in section 4.9 and 5.5 for review today, we're just going to work on some of the basic integral forms. So if you don't have these committed to memory, you need to do so. Flashcards are key. I will not give you the basic integral forms on your tests. Okay, so make sure you practice with those, and we'll practice with them in class too. Okay, so let's just get started. What if I asked you to integrate 5x to the 4th minus 3 over the square root of x plus 2 over x minus 4? What do you think the first thing is that you would do?
Do we separate all of them?
Exactly, we would integrate them separately. And what would we need to do to this 3 over the square root of x?
Get the square root out of the denominator.
Exactly. Instead of writing it as the square root of x, remember our basic integral rule for x to a power is the integral of x to a power dx. And remember, this is the anti-differentiation process. It's the inverse of the differentiation process. If we were taking the derivative, we would multiply by that exponent and then take x to the original exponent minus 1. And so for the inverse process, we do opposite things in opposite order. So we would add 1 to the exponent and divide by the new exponent. Now that's, of course, as long as the exponent is not -1. We'll talk about what happens when when we have a -1 exponent in just a little bit. But the point is, this integral form is written as x to a power, not in radical form. So one thing I would do is make sure any radicals that I have here are written as exponents. So quick review. If you have the mth root of x to the n, remember that can be written as x to the n over m. And if you have 1 over x to a power, that's the same thing as x to the negative of that power. So this is just a little reminder about how radicals work. So if we were going to rewrite this, this would be the integral of 5x to the fourth minus 3x to the what power? The square root is x to the 1/2. And since it was in the denominator, to write it without fraction form, that would be to the negative 1/2. Is everybody okay with that part so far? All right, and so then we would have 2 over x is 2x to the minus 1, and then minus 4. Now, technically speaking, when you're integrating a long string of terms that are being added to or subtracted from each other, you take the integral of the first term, then you add or subtract the integral of the second, plus third, fourth, so on and so forth. We don't typically write it down as breaking it into, say, 4 separate integrals, but that's really what we're doing. So in this case, we're going to integrate 5x to the fourth. We would have 5 times, because remember the integral of a constant times a function is that constant times the integral of the function. To integrate x to the fourth, we will add 1 to the exponent and divide by the new exponent. Then we'll have minus 3 times x to the, when you add 1 to the exponent here, we'll have negative 1/2 plus 1 is positive 1/2. And divide by that new exponent. Now this next one, 2x to the minus 1 is a bit different. I can't add 1 to the exponent and divide by the new exponent because I would be dividing by 0. So can anyone remind me whose derivative is 1 over x?
The natural logarithm.
Yes, excellent. So remember the integral of 1 over x is the natural log of absolute value of x plus c. So we would have 2 times the natural log of absolute x minus, what's the integral of just a constant dx? Or specifically in this case, minus 4 dx.
I'll be 4x.
Perfect.
Yep.
So that would be a 4x plus c. Then we'd go through and simplify, and we would get x to the 5th minus 3 divided by 1/2. 3 divided by 1/2 is the same thing, remember, as 3 times 2. So that would be minus 6x to the 1/2 plus 2 ln absolute x minus 4x plus c. And notice, and remember, I know you've done this before, but we only put 1 plus an arbitrary constant at the end instead of putting, you know, plus C1, C2, C3, and so on and so forth. Does that look familiar to you?
Yes.
I have a
Excellent.
question real quick.
Yes.
I know we're just starting, but for the tests, you always like the simplified version or you don't really care?
Sometimes I will ask you for the simplified version. Most of the time, I really won't care. But as far as if you're talking about multiplying coefficients together, I would expect you to multiply the coefficients together.
Okay, awesome.
Yeah. Now, one thing I wanted to bring to your attention is here where we divided by this new exponent, dividing by 1/2, particularly when I have fractional exponents there, instead of writing this as dividing by the new exponent, I write it and think of it as multiplying by the reciprocal because it saves me time there. So instead of dividing by 1/2 here, most of the time I would write that as multiplication by 2, just to save myself one algebraic step. And we'll do some of those here in just a few minutes. I just wanted to kind of bring that to your attention. Okay, so what about this second example? Do you have any idea what we would do? I'm gonna do something wrong, okay? So it's not equal to this, but I want you to tell me what you think I might have done wrong. So could I make this 1/4 x to the 4th times 4 1/3 x cubed minus 3 times 1/2 x squared? So I just integrated x cubed with respect to x, and then I integrated both of these terms, and then I'm just going to multiply them together. Why can I not do that?
Did you have to undo the chain rule?
I have to undo the chain rule, and I would have to undo a product or a quotient rule. Remember when you took the derivatives of products and quotients, it wasn't just the derivative of the product is the product of the derivatives. We had the product rule, right? And so integrals of products and quotients are also not quite so cut and dried as just sums and differences. We will, in early chapter 8, talk about a method for reversing the product rule. But at this point, with our basic integral forms, we only know how to integrate things that are added to or subtracted from each other. You know, we have this fairly substantial list of things we know how to integrate, but these are because, like the trig functions, for example, we know how to integrate those because those are the derivatives of a known trig function. So if I take anything of these forms and add them to each other or subtract them from each other, I can integrate them term by term. But multiplying or dividing, I have to do something different. So I can't do this. So what we ask ourselves is, how could we go about simplifying that integral so that I could integrate it term by term? Any suggestions?
Distribute.
Distribute. Good. If we just multiply this out, that would be x to the 3rd times 4x squared would be 4x to the what?
6.
Go back a little bit. What do we do with these exponents?
Oh, add 5.
Yeah, add. Oh, that's okay. Remember, when you take a power, x to a power times x to another power, that's when we add the exponents. And when we take a power to a power, that's when we multiply them. Okay, so here we're just multiplying the same base to different exponents. So we would add, and then we would have minus 3x to the 4th dx. And now I have two things that I know how to integrate that are just being added to or subtracted from each other. So we'll integrate term by term, and we'll have 4 times the integral of x to the 6th, x to the 5th is x to the 6th times the reciprocal of that new exponent is 1/6. Then we have minus 3 times the integral of x to the 4th with respect to x is x to the 5th times 1/5. So we have 4 times 1/6, or 2/3 x to the 6th minus 3/5 x to the 5th, and then plus c. The moral to this story is, remember, just like with the product and quotient rules for derivatives, you cannot take the integral of a product of two functions or a quotient of two functions as just the product or quotient of those two functions. You have to do something else. Right now, the only thing we know how to do is to simplify the integrand first, and we'll get some more maybe sophisticated techniques a bit later. Same problem here, except instead of having a product of functions, I have a quotient of functions. So how could I rewrite this? I just separate this fraction. Several ways you could go about doing this algebraically. For me personally, since there's just a single term in the denominator, I would think of this as 7x to the 4th over 5x minus 3x squared over 5x dx. In other words, break up that fraction across addition or subtraction in the numerator, which would be 7/5 x cubed minus 3/5 x dx. Integrate term by term, and we'll have 7/5 times 1/4 x to the 4th minus 3/5 times 1/2 x squared plus c. Is everybody okay with that? Are you okay with the algebra?
Could you move it over slightly to your left so we can see the whole thing?
To my left. Okay. What can you not see? I am so sorry because on my screen it shows it all.
Yeah, no, you're centered for me.
Oh, I don't know. For me, it's a little. Oh, there we go. I fixed it. Never mind.
Okay, sorry. I was like, I don't know what I was doing. All right. There is another option, and it just depends on what you prefer. There's not one correct way to rewrite this function. As far as you could have said that's the integral of 7x to the 4th minus 3x squared times 1/5 x to the negative 1, if you wanted to, and then just distribute that. And you would still get, 7/5 x to the 3rd minus 3/5 x dx, but it bringing it up and multiplying it through instead of separating the fraction would be another option. And you could also factor that 1/5 out front if you wanted to. So as long as you're doing algebraically legal simplification, you'll end up in the same place. All right. So what about some of our favorite trig functions? Whose derivative is secant x tangent x with respect to x? You take the derivative
Secant
of blank.
x.
Secant, excellent. So the integral of secant x tangent x dx is secant x because the derivative of secant is secant tangent. So we would have 2 secant x minus 2 times what function's derivative with respect to x is secant squared x?
Tangent x.
Tangent x, excellent. And then what? Is there one whose derivative is cotangent x, cosecant x?
Cosecant?
Almost. What do we have to do with the plus or minus sign?
Oh, negative cosecant?
Perfect. So if you take the derivative of cosecant, you get negative cosecant cotangent. So if you integrate cosecant cotangent, you would get the negative of cosecant. Good job. Right? Are they starting to come back to you a bit?
Little.
A little bit. I know it's been at least a week or two, hasn't it? Okay, now this one is a bit different. And it wasn't on the list on the front page. It is, I put it a little bit later. But can anyone tell me what this one is most closely related to?
Is it tangent minus 1?
Tangent inverse. It absolutely is. Good job. What we know actually is if you take the derivative of the inverse tangent of x, we get 1 over 1 plus x squared. Okay. Now this one you go, well, there's a 25 down there, but could we factor that 25 out front? Yeah, we could. We could make this 6 over 25 times the integral of 1 over x squared plus 1 dx. And with that factorization process, the integral part now exactly fits to take the integral of 1 over 1 plus x squared and get our tangent x. Since this is true, we know that the integral of 1 over 1 plus x squared dx is the inverse tangent. So we would just have 6 over 25 times the inverse tangent of x plus c. And I know you guys already know this, but just remember when you're doing this exponent, it looks like an exponent -1 for trig functions. That doesn't really mean the -1 power for trig functions. Notationally, if I wanted to put the reciprocal or tangent of x to the -1 power, I would just call it cotangent x. Remember, because we have reciprocal functions for every trig function. When you see that -1 power with a trig function, when the -1 is in the place of the exponent, that's the arc tangent of x, or the inverse tangent of x. Okay, if you take tangent of x all raised to the -1, typically these two things, for any other exponent, these two things would be the same, but for the -1 exponent, they are not. If you take tangent of x all to the -1 power, that's 1 over tangent x, which is cotangent x. Specifically for the -1 in the exponent position, is not a -1 power for trig functions. It's the inverse function. Okay. All right. And we'll deal with these a whole lot more as we go on. I just wanted to kind of give you a reminder as far as the notation is concerned. I want you guys to take a think minute and see if you could integrate this function for me. I'm going to try to be quiet for a minute or two and see what you think. Okay. And if I'm still quiet when you,
I'm not sure I understand.
apparently Siri's talking to me today. If you get an answer and you wanted to say got it or something like that, then I'll know that we can get started looking at it. You are fast, Christian. I'm gonna give everybody just a couple more seconds. All right, it looks like people are beginning to get done. What did you do to this integral before you integrated?
I separated it into 3 over x as one thing, and then plus 1 for the second.
Perfect. Excellent job. So you just broke your fraction apart, and we've got 3 over x plus x over x, which is 1, and then integrate it separately. What would we get when we integrate 3 over x dx?
3 ln x.
Don't forget your absolute value, but yes, good. And then plus
X.
Perfect.
And then
Absolute. Good job. Anybody else get that?
Yes.
Fantastic. Okay. Just because sometimes I said, like I mentioned earlier, I feel kind of like we end up talking to the wall here. If you are in class right now and you didn't just turn on Zoom and then go on your merry way, I would like for you to type here in the chat. All right, thank you. A lot of y'all are just quiet then, in other words. That's perfectly fine too. All right. Sometimes we have things that don't quite match our basic forms. We have those 17 things that we know how to integrate from our basic forms, but maybe it's close, but not quite. What did we do? We do Now, what are we doing with substitution? A lot of times we just call it U substitution, but when we're doing a substitution for an integral, what we're trying to do is take an integral that kind of resembles something that we know how to integrate, but maybe doesn't quite match up, and make it look like something that we know how to integrate. So how do we go about doing that? Well, it depends on what you're trying to get to. Okay, so this is one of the many reasons that it's so important for you to know those basic integral forms, is because if you have something that kind of almost matches but doesn't quite, you have to know what you're trying to match it with before you know if you've got it. So, for example, if you have a function where part of it is the derivative of the other part is typically what we choose for a substitution U. So what we're going to do is look at this and go, okay, this looks most closely related to, out of those 17 things that we know how to integrate, this looks close to something like U to the m du. Now, technically speaking, could I just multiply this out and distribute? Yeah, it might take me a while, but it's just to the 4th power. I could do that. Now, if it was to the 14th power, it would take me a bit longer. And if it was to the 1/4 power, that wouldn't be an option anymore. So what we want to do is practice doing substitutions so that we can rewrite an integral that is related to one that we know how to integrate and put it in the appropriate integral form. Okay. So the parts of my function, I have a 2x and I have an x squared plus 3 that is being raised to a power of 4. Is one of these bits the derivative of the other part, at least up to a constant multiple? It may, we may have to have an adjustment for a constant multiple, but as far as derivatives are concerned, which one is the derivative of the other?
Derivative of x squared.
Good. 2x would be the derivative of this quantity x squared plus 3. So the part that we're going to choose for U is the x squared plus 3. Sorry, my pen just went a little weird. And so we're going to rewrite this entire function inside my integral as a function of U. And that includes the dx as well. So once we have made our substitution, we're going to say, okay, how am I going to get rid of this dx in favor of something in terms of du? Well, if u is equal to x squared plus 3, then du dx would be 2x, right? Just the derivative. And so du would be 2x dx, simply by multiplying both sides by dx. So if I take this chunk and this chunk of my original integral, those two pieces combined are nothing more than the differential of u if I made this substitution. So my integral in terms of u would be u to the 4th, and all the rest of that stuff would just be du. Is everybody okay right here? Any questions up to this point? All right. Do we know how to integrate this? Of course we do. That's just our basic u to a power du. So we would have 1/5 u to the 5th plus c. And then since our original integral was in terms of x, we back substitute what u is in terms of x and write our final answer as 1/5 of x squared plus 3 to the 5th plus c. Now, we haven't done this up to this point, but could we check our answers? Well, sure you can. If this is the indefinite integral of this function up here, if I take the derivative of this function, I should just get the integrand part. So if you take the derivative of 1/5 x squared plus 3 to the 5th plus c, that would be 1/5 times 5 times x squared plus 3 to the 4th times the derivative of x squared plus 3, which is 2x, and then the derivative of any constant is 0. So we would end up with x squared plus 3 to the 4th times 2x. And so we've checked ourselves with differentiation. Now notice, the more you have to do to rewrite the original problem before you can integrate it, kind of the more you would have to do here to check yourselves with differentiation, because there might be a lot of rewriting going on, but you can. If you take an indefinite integral, then take the derivative of your answer, you should get something that is equivalent to the integrand of the original problem.
I have a question real quick.
Yes.
For the answer, are you okay we put like the whole thing that's in parentheses, like over 5 to the 5th power plus 6 plus c?
Oh, so just write it as that?
Yeah.
Oh, that'd be perfectly fine.
Cool.
Yeah. All right. So most of the time, about this time of class, all right. Are we ready to get started again?
I guess.
If you must, huh? All right. So, you know, when you're trying to determine what to choose for you, as I mentioned, if you have things that are multiplied together, anything like that, and you see that one part is up to a constant multiple, or quote, almost the derivative of the other part, then the other part is typically u. A lot of times, if there's a fraction involved, most of the time when that's the case, we try taking the u from the denominator. But keep in mind that once again, if I look at what's being raised to a power in the denominator, so not including the overall exponent, the derivative of that involves an x to the 4th, which is right up here. So here I would choose u to be 9 minus 7x to the 5th. And go from there. So we would have du dx would be negative 35x to the 4th, or du is negative 35x to the 4th dx. Now, most of the time after today, I won't typically write in this middle step, but this is just a reminder of where we're getting du. And here, it kind of depends on who your Calculus 1 teacher was, what you do next. Everybody has their own personal preference, and there are several ways we can do this that would be correct. You can say, all right, I'm trying to rewrite this in terms of u, so I could solve this for dx. So dx would be du over negative 35x to the 4th, and then just plug it in. So we would have the integral of 3x to the 4th over 9 minus 7x to the 5th, remember, was u. So this would be u to the 1/2 power because of the square root, times dx is du over negative 35x to the 4th. And then if all of the other x's cancel out, we're good to go. If they don't, we have to back up and try a different substitution. But this one cancels with this one, and we would end up with, when I factor the constants out front, we would have a negative of 3 over 35 times the integral of du over u to the 1/2. Or that would be negative 3 over 35 times the integral of u to the negative 1/2 du. At which point we can just integrate. Integral of u to the negative 1/2 du is u to the positive 1/2 because negative 1/2 plus 1 is positive 1/2. And then multiply by the reciprocal of that new exponent. Remember, the reciprocal of 1/2 is 2 over 1 or just 2. So that would be a negative 6 over 35 times u to the 1/2 plus c, or negative 6 over 35 times 9 minus 7x to the 5th to the 1/2 plus c. Now, for me personally, whether you leave that as a 1/2 power or a square root doesn't make any difference at all to me. I don't have, it's fine if you leave it as an exponent rather than a radical for my purposes. A lot of times in the textbook, if you're looking at, examples and stuff in the textbook, if they started out with radicals in the original, they'll typically write their answer in terms of radicals rather than exponents. But as long as it's equivalent, it should be good. Okay. Any questions about that one at this point? Okay, that's,
Something real
oh,
quick.
go ahead. Go ahead.
Where do you grab the 2? In front of the u?
Here.
Yeah.
Okay, remember when you integrate, you add 1 to the exponent, which would give me a positive 1/2. And then you divide by that new exponent, or that's the equivalent of multiplying by its reciprocal. So I'm doing that's division by 1/2.
Oh, okay.
Now, oh, go ahead. I'm sorry.
Oh, I just said thank you.
Oh, you're welcome.
Got it.
One of the things that, this is a perfectly reasonable way to do this problem, and a lot of people prefer it to the other method. Personally, when I get to this point and I say, okay, I've got the integral of 3x to the 4th over the square root of 9 minus 7x to the 5th dx. When I chose my u to be 9 minus 7x to the 5th, and I get that du is negative 35x to the 4th dx, instead of doing this part, what I would probably do is multiply by negative 35 and reverse it with a negative 1 over 35 out front. That gives me a du right here, because I have a negative 35x to the 4th dx. I have an extra factor of 3 that I can pull out front because it's a constant multiple. Remember, you can only factor constants out in front. If it's the variable of integration, it can definitely not be factored in front of the integral sign, but that would give me du over u to the 1/2. Just as we got here, but in a slightly different order. Now you go, well, I like to do it this way, so why do I have to look at it this way? Or vice versa. As a calculus student, depending on where you go from here, are you going to calculus 3? Are you just going to some other engineering classes? What's happening here? Depending on who your teacher is, we all have our favorites. I do it this way most of the time because it's the first way I learned. Some people prefer this way. You need to be able to understand what someone's doing when they do it either way. And of course, everybody in here will have their own personal preference, but either method is perfectly fine, and you need to be able to follow through and understand it either direction. And so I'll try to do some of them one way and some of them the other, just to kind of keep you, keep it fresh that you can do it either way. But there are multiple options there. Now notice once we did that, multiplying and reversing, basically what have I done? I've multiplied by 1 because I multiplied by negative 35 and negative 1 over 35. The product of those two is 1. So I haven't changed the integral there. I've just rewritten it. Okay. All right. Any questions up to this point? Okay. So what about this one? Well, what do you think I would choose for you?
Three x plus 2.
Plus
3x
two.
plus 2. There's not a whole lot of choice there, is it? You know, it's most of the time when you have a fraction, the u will come from the denominator. We'll talk about some specific some specific examples of when that's not true here in just a minute. But in this case, I would just let u be the 3x plus 2. And so du would be 3 dx. Now remember, how do we get that? We take the derivative of u with respect to x and then just move the dx over. So particularly in this case, I need a 3 dx for my du. So I'm just going to multiply by 3 and reverse it with a 1/3 out front. And so that 3 dx on the inside is my du. And I will have 1/3 the integral of du over u. Or remember, that's the same thing as 1/3 times 1 over u du. Whether I write my du in the top or out here as a product to the side, it doesn't matter. You'll never have du in the denominator of your fraction. Now your du may come from the denominator sometimes, but it will never be actually in the denominator once you have written the problem. And the integral of 1 over u du is the natural log of the absolute value of u, or we would have 1 over 3 times the natural log of absolute 3x plus 2 plus c. So for you personally, how many do you prefer multiplying and reversing, or do you prefer solving for dx, or do you have a preference?
I think dx for me.
No preference thus far.
I muted myself, and then it just takes a while. You know, it just depends on what you prefer to do. Now, if we have a fraction, when are we going to perhaps not choose just what's in the denominator? If there is a natural log involved in your integral, it is probably going to be u, at least with what we know now. And that's no matter where it is. No matter if it's in the numerator or denominator. So for example, I didn't put one down here, but let's say we had the integral of ln x over x dx. Notice that in this case, if I used what's in the denominator with u is equal to x, well, it'll never do you any good if you choose u equal to x, because you literally will just be rewriting the problem with u's instead of x's, but you'll have exactly the same thing. But notice here, I have a natural log that's in the numerator. So I would choose u to be the natural log of x. So du would be 1 over x dx. So this whole chunk right here, no rewriting necessary, but that whole chunk right there would just be du. So that would be the integral of u du, or 1/2 u squared plus c, which is 1/2 natural log of x quantity squared plus c. Okay, and once again, if you just kind of keep, Nicholas, we're not quite to Lie yet. That would be something when we're doing integration by parts, which won't be till chapter 8. Right now, it's just plain u substitution. we don't, you know, typically do that. You can kind of keep it in mind though, definitely. Let me think what else I was going to say. Oh, what I was going to say is just keep in mind when you're choosing your u is you still want to choose the part whose derivative is already in there. And in that case, you know, you think of natural log of x and the derivative is 1 over x, which you have. So that gives you an idea as well. Also, if you have exponential functions, most of the time, if you have only a single exponential function, the power to which it is raised is typically u. Now, these are, you know, you'll notice when I say it, it's typically or a good first guess, because there are infinitely many possibilities about the integrands. And so I can't say this will always work because it depends on what else is in there. But if I have an exponential function and there's other stuff going on there, most of the time, if there's only a single exponential, the exponent to which it is raised is u. So in this case, we'd try to let u equal sine x. So du would be cosine x dx. And lucky for us, that's just sitting there waiting to be du. So this would be the integral of e to the u du, which is what? Whose derivative is e to the u? That's the derivative of what function?
E to the
Itself,
u.
right?
Itself, exactly. And we love e to the u because it's, I mean, it's its own derivative, it's its own integral, it's fabulous. So the integral of e to the u du would be e to the u plus c, or in terms of the original variable, that would be e to the sine x plus c. Now, we'll do a lot of u substitution in various different types of problems, but there are some problems that we can kind of generalize and make life a little bit easier on ourselves. For example, when instead of having just an x in there, you just have a constant times x inside a trig function or an exponential, something like that. If we went through the u substitution, what do you think I would choose for u for that problem? Remember, we know the integral of sine u du is negative cosine u plus c. So what do you think I should choose for u to make it match up with an integral form that I know? Is anybody out there?
Yes.
Okay.
5x.
5x, exactly. What's in the place of the u here? It's what you're taking the sign of, right? So let's just choose u to be 5x. So du would be 5 dx. Now, I would probably multiply by 5 and reverse with a 1/5 out front. So in essence, I've multiplied by 1, and this part would be my du. So I would have 1/5 the integral of sine u du, or 1/5 times negative cosine u plus c. Or let's just simplify it a little bit. That would be negative 1/5. Cosine u would be cosine 5x plus c. If that had been a sine of 7x, what do you think would have been the difference in our problem here? Instead of having 5s, we would have 7s. Or in general, if you just have a constant multiple of the variable of integration inside a trig function, so if you have the integral of sine of ax dx, where a is a constant, You can go through this u substitution, and that's perfectly fine. You'll get there, but it will always just be negative 1 over a cosine of ax plus c. Because if I just replace that 5 with an a and did the same problem, that's what we would get. Okay, so for example, and that would be true if you had a sine or a cosine or a tangent or anything like that. So what do you think we would get if we took the integral of secant 3x tangent 3x dx? Well, ask yourselves, whose derivative is secant tangent? If I take the derivative of blank, I get a secant times a tangent.
Secant.
Secant. So we have a 3x in there. This would be a 1 over 3 secant 3x plus c. Now, could you instead go through and use u equal 3x and get the same process? Absolutely. But for some, very close to basic, but a little bit of difference in that we have a constant multiple, we can kind of skip the u substitution if we know the process. Okay, so same thing is true when you take e to a constant times x. The integral of e to the ax dx will be 1 over a e to the ax plus c. So the integral of e to the 3x dx would be 1/3 e to the 3x plus c. Okay, but it's okay if you go ahead and go through and set u equal to 3x and just go through the process. You'll get there. It just may take you a little bit longer. The reason we're talking about these generalized forms is because we do problems like these so often that it gets a little bit time consuming to have to write down the u substitution for the constant multiple ones. But it is still fine if you do that. All right, so let's look at inverse trig integrals. Okay. These were the last 3 integral forms that I told you that we would have a little bit later. These guys, if you'll notice, don't exactly match up with what we think of when we think of the derivatives of our inverse trig functions. For example, if you take the derivative of the arc tangent of x, that is 1 over 1 plus x squared, right? So these guys, while they're kind of close, they're not exactly the same. We have something that may not just be a 1 there, and this may not be just an x or just a u. So when we go through and say, let's say we have something like the integral of 1 over a squared plus u squared du. So a more general form for something that looks similar to an inverse tangent integral. I'm going to derive one of them, and then we're just going to use the others because the process would be very similar. If you wanted to put this and make it look like an integral form for an arc tangent, because we know that the integral of 1 over 1 plus u squared du is the arc tangent of u. I could have used x's there or w's, whatever variable you wanted. I want to make this look like that. Okay, so what I'm going to do is I would factor the a squared out front. So this would be 1 plus u squared over a squared du. Okay. Now, this is assuming that a is a constant. So I'm just rewriting it algebraically. So this would be a 1 over a squared times the integral of 1 over 1 plus u squared over a squared could be written as u over a all squared du. Now, I'm going to change this to a W just so it'll be a different variable up here when we're looking at it. It doesn't matter what I call that. I could call it X, W, T, whatever. But if we have 1 plus a variable expression squared in the bottom and just a 1 times the differential in the top, that's an arctangent. So I'm going to do a substitution, but don't think that it always has to be a U substitution because I already have U in my problem. I can call my new variable whatever I want to. I'm going to call it W this time. If I'm trying to make this match this, what is being squared here is U over A. So dW would be 1 over A du. Because remember, U over A is 1 over A times U. So when you take the derivative with respect to U, you just get 1 over A. And then I just move the du over there. So I would multiply by 1 over A inside and the reciprocal of that outside. This part would be my dW, and I have A over A squared is 1 over A times the integral of 1 plus W squared dW, where we have 1 over A times the inverse tangent of W plus C, or that's 1 over A times the inverse tangent of U over A plus C. Now, I go through that one to say, we don't want to have to do that every time, right? That's a lot of factoring out and adjusting of constants and things like that. So while you're memorizing your basic trig formulas or basic integral formulas, these 3 you're going to need to know with the more generalized version so that you don't have to go through this process every single time. Okay. Notice there is not a 1 over A out in front of the arc sine function, and that's because if we go through this process, the A and the 1 over A will cancel each other out. But there is one in front of the arc tangent and the arc secant. So add these to your flashcard list unless you want to have to go through and factor out the constants every single time. So what would we get if we had the integral of 1 over, I think I may have one on the next page. Let's do this one again. Let's say we have 1 over 9 plus 25x squared dx. First question, is that most closely related to an inverse sine, an inverse tangent, or an inverse secant?
Tangent.
Tangent. Why? Well, first of all, we don't have a square root here, right? But the bigger thing is that we have the constant and the variable expression being added to each other. In both the arc sine and the arc secant formula, those guys have a subtraction sign. Okay? So if we're trying to use the integral of du over a squared plus u squared, that's 1 over a arc tangent of u over a. We just derived that formula. What would we choose for a? A will be the square root of the constant part. And we'll take the non-negative square root or the principal square root. So a will be 3. And u will be the variable expression that is being squared here. So u will be 5x. Okay. Now, be careful. We do still have to follow through with this u substitution. If u is 5x, then du is 5 dx. So to get my du, I would need to multiply by 5 and reverse it with a 1/5 out front. And we would have 1/5. The integral of this chunk right here is du over a squared plus u squared. So that would be 1/5, using our formula from here. 1 over a would be 1/3 arc tangent of u over a would be 5x/3 plus c. Questions? Not at this second. All right, so I want you to try one. Now I'm going to put the 3 basic forms right down there. Which one of those 3, 18, 19, or 20, does this most closely resemble? Do you think it's an arc sine, an arc tangent, or an arc secant?
Sine.
Sine. And remember, to figure that out, key on the fact that it's a variable, I mean, a constant minus a variable. Okay. If it had been a variable minus a constant there, we would be talking about an arc secant. So I need you to identify what is A and what is U. What do you think A is in this
A
particular
would be
book?
3.
A would be 3. Good. And U would be
4x.
4x. Perfect. So I'm going to give you guys a couple minutes to go through the U substitution to get this one right, and then we'll compare. And while I'm thinking about it, Nicholas, will we have these sheets available to print them out? Do you mean the fill-in notes? I sent those to you, or they're in Canvas under modules? All right, are you ready to compare? Or at least look through it? If u is equal to 4x, okay, so what would that mean about du? If u is equal to 4x, then du will be 4 dx. So I'm just going to multiply by 4 and reverse it with a 1/4. You could definitely solve for dx and plug in, and that's fine. But this would be 1/4 the integral of du over the square root of a squared minus u squared. So that is 1/4 the inverse sine of u over a would be 4x/3, and then plus c. Did anybody get that?
It's almost there.
All right. Any questions? Okay, well, what about definite integrals? Remember, indefinite integrals, which is what we've been doing, we're finding a family or class of functions whose derivative is equal to the original integrand. Okay, wait, let me back up. Nicholas, do you see what went wrong? If you said no, that you didn't get that one, do you know what happened? Or if you didn't get that, if anybody has a question, let me know and I'll. Oh, okay. Never mind. Sorry. Didn't have any questions. All right. So for indefinite integrals up here, remember we are finding a class of functions or a family of functions called antiderivatives whose derivatives equal the original integrand. When we're doing definite integrals, we actually get a numerical answer. And remember that numerical answer is, and we'll talk more about this later, but that numerical answer is equivalent to the net area between that graph and the x-axis over the given interval. But my question at this point is, how do we compute these definite integrals? Remember, what we do is we do the indefinite integral part. The integral of secant x tangent x is just secant x. Integral of secant squared x is tangent x. And then we say, okay, and we're going to evaluate that from 0 to pi over 4. Remember, we're using what we call the fundamental theorem of calculus, where we take the indefinite integral, and then what do? We plug in the top limit and subtract what we get when we plug in the bottom limit. So we would have the secant of pi over 4 plus the tangent of pi over 4 minus the secant of 0 plus the tangent of 0. Does it matter which limit you plug in first?
Yes.
It absolutely does. You always plug the top limit in and subtract what you get when you plug in the bottom limit. If you plug them in backwards, remember that changes the sign of your answer. So you do have to go in the correct order. What's the secant of pi over 4? Well, remember, the secant of pi over 4 is 1 over the cosine of pi over 4. From our unit circle that I know you all have memorized, the cosine of pi over 4 is the square root of 2 over 2. Reciprocal of that would be 2 over the square root of 2, which is the square root of 2. Secant of pi over 4 is the square root of 2. Tangent of pi over 4, sine and cosine have the same value at pi over 4. So tangent sine over cosine, so that would be 1. Secant of 0 is 1 over the cosine of 0, and the cosine of 0 is 1. So secant of 0 is 1, tangent of 0 is 0. So we end up with the square root of 2 plus 1 minus 1, which is the square root of 2. And you will need to be practicing to find exact answers for those. Most of the time it'll ask you for an exact answer on a problem like that in MyMathLab, and I usually will ask for exact answer as well. Just keep in mind though, whether you are, if you have a hard copy of the textbook, the unit circle is on the back of the first page of the book. And I think you can also find it under the ebook as well. Now, if you are doing a use substitution problem and you're doing a definite integral, you've got a couple of choices again. So go with option 1 here. And this is kind of like, do you multiply in reverse or do you solve for dx? You want to be able to follow through and do either method because different people will do different methods and you want to be able to do it as well. Okay, so let's not worry about the definite integral part right now. Here, first thing we have to do is determine what we would choose for u. Any suggestions?
X squared plus 4.
X squared plus 4 would be awesome. If we let u be x squared plus 4, then du would be 2x dx. So in terms of u, the integrand would be, oh my goodness, I left off my dx, which is not good. Got to have a differential up there to know what we're integrating with respect to. So that would be du over u squared. Now, option 1, I am going to leave my limits as x limits. So now I wouldn't necessarily have to write down x equals 0 to x equals 1. I'm really just writing the x equals part for emphasis to remind you that these are still x limits. So you can go ahead and do your integration, which would be the integral of u to the negative 2 is negative u to the negative 1. Okay, because remember, a du over u squared is the same thing as u to the negative 2 du. So when you add 1 to the exponent, you get negative 1, and you divide by the new exponent, you get negative 1 out front. If I did not change my limits to u limits, I would have to then back substitute what u was in terms of x. So that would be the negative of x squared plus 4 to the negative 1 from 0 to 1. So just like we've been doing with indefinite integrals, if I don't change my limits, I have to replace u with what it is in terms of x before I plug in top and bottom limits. So I have negative 1 over x squared plus 4 from 0 to 1. And now I'm just going to plug in the top limit and subtract what I get when I plug in the bottom limit. So that's what, negative 1/5 plus 1/4. So negative 4 over 20 plus 5 over 20 is 1 over 20. Okay. Perfectly reasonable way to do this problem. It's just fine. There is another option though, as far as it all depends on when you plug your limits in for u. Here, we did it similar to what we've been doing with indefinite integrals and waited until the very end and replaced u with what it was in terms of x. The other option is up here when you say, okay, if u is equal to x squared plus 4 and du is equal to 2x dx, and we get the integral of du over u squared, we can also go ahead and plug our limits into u here. Our first limit for x was 1. If x is equal to 1, that means that u is equal to 1 squared plus 4, which is 5. Our original lower limit was x equals 0. So that would mean that u is equal to 0 squared plus 4, which is 4. So in terms of u limits, this would be a u limit of 4 at the bottom and 5 at the top. So basically what I did was the work that I did down here in the previous problem when I replaced x with 1 and x with 0, I already did it up here. If you change your limits to u limits, you never have to go back to x's again in that problem. You've already done that substitution that we did down here. We already did it up here. So we would have negative 1 over u from 4 to 5, which is negative 1/5 minus a negative 1/4, which is 1 over 20. You get the same answer. It is simply a matter of when you plug the x's in to u. And it is totally a personal preference. You can do it either way. I know this one looks a little bit shorter, but that's just because we had already done the integration part here. And so, it's really 6 and 1/2 dozen together a lot of times, but this one does feel a little bit shorter. Plugging them in earlier rather than later makes it look a little bit neater, I think. But you want to be able to do it either way, or at least